And then we move on to the next chapter, which is, next section, which is section 3.5, is the implicit differentiation. Now, everything we had seen was the explicit equation or explicit function, which the function identified as y is a function of x, right? So everything we have x as input, we only have one y, right? But for the implicit equation, we're also able to do the derivative, right? But the basic idea is, well, y could be forming into the expression of x, so it's still able to find the derivative of y respect to x, but it's a little bit other way to do, right? It's not only just the expression is separated nicely with x to be a function of y to be a function of x, but it is like x and y are together inside an expression. That's called the implicit equation. And the way to differentiate it is called implicit differentiation. Well, the basic idea is, well, y is a function of x. So our y here may be in the implicit function, such as, for example, the unit circle. I know more that y is an expression of x, but y is somehow also a composite function involving inside the equation here. Right? So we need to face something to take the derivative of, in order to take the derivative of y with respect to x, we need to have, say, face something like we have a function of y. Right? So by the rule of y is a function of x, we need to take is the g prime of, illustrate that right that way. That is g of f of x, and when we apply the chain rule, that's g prime of f of x multiply f prime of x. Right? In other words, right, if this one go back to the formula, that's g prime of y multiplied by y prime. Right, since, in other words, right, still, that we take the derivative of the expression of y in the same way as we take x, but just need to attach the y prime afterwards, where y prime stands for just dy over dx. Y prime is dy over dx. That is the expression that will leave something clean derivative of x, but we'll have something this is the function of x, that we're able to differentiate the y over x, but differentiate the expression first, multiply by dy over dx. Then at the end, when we do some algebra, we will get the dy dx, or the derivative of y respect to x, as an expression of maybe not only the x, but also the y. So that is the basic idea of the implicit differentiation. Then we try to see some example. The basic idea is to apply the chain rule. Right? The chain rule is usable over there because y is able to write as a function of x, but we just don't write it as a function of x. Keep it as implicit function. For example, when we illustrate the formula of the logarithmic, right, it's inside one step, we'll see that e to the y equal x. Of course, expect us to do different way, but as we call talking about the implicit differentiation, are able to find the derivative on both sides of the equation. Right, so we take the derivative on the left, that is we see much careful of the step what we are doing, right? That's we're doing the derivative of x respect to x of e to the y respect to x on the left side, and derivative of x respect to x on the right side. Right? That's what we're doing. So e to the y, as we apply the chain rule, that's still e to the y, multiplied by the dy over dx. On the right side, derivative of x respect to x is 1. Therefore, our dy over dx you could write it as e equals 1 over e to the y, or we given e to the y is x, so dy over dx is 1 over x is also appropriate. Right, so that is how we do the implicit differentiation. Every time we have the expression of x, we differentiate the same way. We have the expression of y. We also do it similarly as we do the differentiate of x, but after the thing, what we do is attach the dy over dx with the expression we have for the derivative. Another example could be shown. Find dy dx for x squared minus 2y to the third plus 4y equals 2. Oh, don't have to show it, we just need to know that we need to find the derivative of every term. Right, so that apply the derivative, we have 2x minus 2 times 3y squared dy over dx. Right, because that's 2 is their coefficient, negative 2, right? We have y to the third, we will apply the power rule, that's 3y squared, multiplied by dy over dx, since that is the expression of y. Every time we have the expression of y involving, we need to multiply by dy over dx. And when we have y over here, the derivative of y is simply just dy over dx. And then we have the constant, which the constant have a derivative of 0 still. What we can get is negative 6y squared plus 4 dy over dx as a factor equals negative 2x. So if we do step by step, right? Negative 6y squared dy over dx plus 4 dy over dx equals negative 2x. We'll move the term doesn't have the dy over dx as the seeking derivative, we move that to the right side, and left over the terms have dy dx as a factor, and we'll factor it out. I have negative 6y squared plus 4 negative 2x. Then the only thing is to solve the variable, the dy dx is the variable, then we just divide. Negative 2x divided by negative 6y squared plus 4 Or if you want, well, we see both of them have negative sign, so you can multiply by -1, multiply this term by -1. That we get, well, 2x as the numerator, denominator -1 times -6y squared, -1 times 4. In this case, we have the expression of x and y as the function of dy over dx. Right, so dy dx is not only depending on the x, but also depending on the y. Right, which means for the original expression, every x value put in maybe could have more than one value of the y. Then the derivative at each point should be different, then depending on not only the x but also depending on the y value of the point. And that's what it means. Try find dy over dx for x equals tangent of y. And that is also an implicit function, even though if you apply the inverse property, that will get arctangent of x equals y. We do not know what is the derivative of arctangent to y, arctangent of x. We don't know it. So, but when we get the inverse function x equals tangent to y, in this case, we're able to find the derivative of x, we're able to find the derivative of tangent, basically. Right, so we take the derivative, 1, my derivative of x is 1, the derivative of tangent is secant squared of y times y prime. Right, so y prime will be 1 over, or you could attach the dy over dx, or same thing as y prime. Right, dy over dx, just a good habit that, well, it will show that is the derivative of y respect to x. Instead of the term we just say y prime, we do not know which variable it respects to, right, to take the derivative. Later on, we will have something else. In the section 7, we'll have, well, not only y is a function of x, but all the variable x, y, or something else are a function of time. Right? The time is varying, then all the variables are varying. Then in that case, right, we do not have just simply have y prime meaning the derivative of y respect to x will mean something else. Right? And anyway, right, that here just be careful, right, that we get 1 over secant squared of x. That is, if we want, we could just write it as cosine square of y. If we want to stop here, that is fine, right? The derivative of y respect to x is a function of y. But recall that, right? So the tangent y is x. If we treat y as an angle, that has the trig value of x over 1. We get a triangle of angle y. We have opposite over the adjacent as the x over 1. Right, and the hypotenuse is square root of 1 plus x squared, or x squared plus 1. it is a little bit benefit to write x squared plus 1 is good. Or you could write square root 1 plus x squared, it's also fine. So therefore we get the cosine of y is adjacent over hypotenuse, that's 1 over square root 1 plus x squared. That is 1 over 1 plus x squared. Right, so that is how we find the implicit differentiation, right, for this one. Of course we can start at the cosine square of y, but it is more appropriate to leave answer like the expression of x if it is possible. Right? If it is possible to make the expression to be a function of x, then we just do that. And that thing 1 over 1 plus x squared is, if we can remember what we have seen, right? We have seen before y is arccotangent of x. That is the derivative of arccotangent x, which is the inverse trig function. You will see what they are. For the function, well, not function, for the equation implicit expression, right, y equal sine xy, we're able to find the derivative. The derivative of y with respect to x is cosine of xy multiply the derivative of xy. And then afterwards we'll have the inside or the chain rule applied, but basically this one inside is a product. Right? So for xy, let u to be x, v to be y, u prime will be 1, v prime will be dy by dx. Right, that is the small product, what it is. Then dy dx will be cosine xy multiply u prime v plus v prime u. And we could expand it a little bit, right? Dy dx is y cosine xy plus x cosine xy dy over dx. And for the variable solving is solving for dy over dx as the variable, so we need to subtract the entire term to the left. Right, so dy over dx minus x cosine y, cosine xy dy over dx equal y cosine xy dy over dx. Then the next step is just to factor out dy over dx. 1 minus x cosine xy equal y cosine xy. Then finally dy over dx, we just divide the coefficient of dy dx on both sides. Right? We have y cosine xy on the numerator over 1 minus x cosine xy. Or simply we get dy dx as this expression. Right. Then let's see the next one. ln xy plus 5x equals 30. Right, for that equation, well, we have ln xy plus 5x equals 30. We can apply the product rule still for the derivative of xy, but since that is natural log, separate them first. Right, so ln of x plus ln of y plus 5x equals 30. Right, then we take the derivative of everything, right? That we have 1 over x times 1 plus 1 over y times dy over dx plus 5 equals 0. Since, well, we have x and the y on the denominator, what we can do is multiply the entire equation by xy. Right, that is appropriate. Right? We do not want the denominator involving somewhere. We could just multiply the common factor of the denominator. Right? And the common multiple is the least common multiple of the denominator. Multiply everything. We get xy over x plus xy over y times dy over dx plus xy times 5. Right, that we get, well, y plus x dy dx plus 5xy equals 0. So the only term has dy dx is the middle term, then everything else will move on the right side. That is negative y, negative 5xy, which is, if we factor out negative y, that's 1 plus 5x. Right, so at the end, if we divide x on the right side, we get dy over dx equals negative y 1 plus 5x over x. Right, so that will be the expression left at the end. Right, dy over dx equals negative y times 1 plus 5x over x. Right, of course, if you do like negative 5 minus 1 over x, then factor to be negative 5x minus 1 all over x, then multiply y, that will get same result. Maybe multiply it has benefit, maybe not. Right? Just depends on what you think. If you directly simplify from this step, then it will be same thing. And if you still remember, right, the dy dx is the geometrically is the slope at a point. Right, so if you have an equation, y to the third plus y squared minus 5y minus x squared equals negative 4. We can find the dy dx and also find the tangent line. At point 0. and the point 1, -3. Right, first of all, of course, if y is 0, x is 2, we get -4. Right, if y is -3, we get -27 plus 9 plus 15. Right, 9, 15 is what? That's 24, 27. That is -3, and -3 minus 1, that's -4. So both points are on the expression. Then we just find dy dx in the first step. We have 3y squared plus 2y y prime dy dx minus 5 dy dx minus 2x equals 0. So we factor out the dy dx for the term has dy dx. That we get 3y squared plus 2y minus 5. And on the right side we have 2x. That we get dy over dx to be 2x over 3y squared plus 2y minus 5. Right, that is the derivative of this expression. I jump a little for some solving if you follow step by step, like move it first and then factor out, you'll get the same result over here. Maybe one step or two I dropped, but still I kept the necessary steps. Right? So at the point 2, 0, we have the slope at the point 2, 0 will be the derivative evaluate at a point. Like we mentioned before, we use that small vertical line dashed next to the expression, and then put subscripts of the point value, right? Not only evaluating x in, but evaluate the y value in, right? And that's what the slope is the derivative at the given point, right? So we substitute x equal 2, y equals 0 into the expression. That is x to be 2, y to be 0. Which is 4 over -5. -4/5. Right, so if we put on the first side, tangent line. If you still remember, I have an equation of line that's y equals m times x minus x0 plus y0 as the equation. Right, the slope at a given point, that is the point slope form. Right, tangent line will be y equals slope times x minus 2 plus the given y value is 0, so the line is y is -4/5 x plus 8/5. Right, that is the first given point. And then also at the given point 1, -3, the slope is the derivative. Two times x over 3y squared plus 2y minus 5. Right, 2 times 1 is 2. 3 squared is 9 times 3 is 27 minus 6 minus 5. 27 minus 11, right? That's 13. And I mean that's 16. Right, 26 minus 11, that's 16. 2 over 16, that's 1 over 8. Right, so the tangent line has equation y equals slope times x minus 1 plus the y value is negative 3. 1/8 x minus 1/8 minus 3. I will distribute it and find the common denominator and factor them and multiply or whatever to combine them together. That's negative 25 over 3 over 8. Right, that is the equation of tangent line at the given 2 points. Right, 2, 0 or at another point at 1, negative 3. Right, so find the derivative and then substitute the point to find the slope. Then use the point slope form to find out the equation of tangent line. Of course, if you want, you could sketch this equation and sketch the tangent line to verify that, well, they are actually attached together. Well, this one looks like a little bit trickier equation, right? That's 3 times 100 x squared plus y squared squared equals 100xy. Basically, the 0.31 is on that. We'll get 3 squared plus 1 squared is 10, 10 squared is 100, times 3 is 300, 100 times 3 times 1 is also 300. We'll just make sure that the equation has no problem. And then, to find the tangent line at a given point, we first of all need to find the derivative. Right? 3 times twice of x squared plus y squared, first power. Derivative of x squared is 2x, derivative of y squared is 2y times dy by dx. 100, and we apply power rule. I believe we have showed it before. Right, u prime v plus v prime u. Right, if you can go back to what we had, right, the derivative of x times y is y plus x dy dx. Right, so we can have like 3 times 2 times this one also can be factored. Right, that's 3 times 4 is 12, x squared plus y squared. Right, and this 12 and 100 can be divided by 4 to get 3 and 25. And we have the term 3x squared y squared times x plus 3x squared y squared times y divided dx is just simply expand that. And then we have 100 over 4 is 25y plus 25x divided dx. What we can do is, well, for the term on the hash dy dx, we move that to the left, and the remaining term we take that on the right side. Right, that we get dy over dx of the expression 3y x squared plus y squared minus 25x, 25y minus 3x x squared plus y squared. That is one small step in this equation, right? For this question, actually didn't ask us to find the dy over dx anyway, right? The question didn't say, well, we need this expression for the dy over dx. Of course, we find the expression for dy dx and substitute in, that's fine. But since we know that x is 3, y is 1, we only want to find the equation of the tangent line, then what we can do is just directly substitute in our point 3 and 1. Right? Even though in this step, after we divide, right, we can already substitute in to see what we will have. It will be a little easier, but let's see the first way, right, to get the dy dx first. (25y minus 3x x squared plus y squared over 3y x squared plus y squared minus 25x). Right, that's long expression, then we could evaluate dy dx at the point 3, 1. X is 3, y is 1, right, so 25y minus 3 times 3 of 3 squared plus 1 squared. That's very long still, right? 3y. And maybe we can make mistakes, right? 3 squared plus 1 squared minus 25x. That we get 25 minus, well, we know that this is 10, so 90. Over that is 30 minus 75. Well, 25 minus 90, that's what? Negative 65 over negative 45. That's 13 over 9. That's the slope. Right, so if we do long step, that will get the slope at the point 31 to be 13 over 9. Right. So we simplify, expand everything to get dy dx off together, and then the expression of dy dx, then substitute the point into that for x value and for the y value. I will get this as the expression, which is pretty much very long. Well, what we can do is, I'm going to erase this part. Since they don't ask for dy dx, right, so what we can do is 3x squared plus y squared, x plus y dy dx, 25 y plus x dy dx. I could just substitute x equal 3 and y equal 1 into this expression. I get, well, x squared plus y squared is 30. right? 25 y plus 3 dy dx. What I get here is, well, 90 equals 30. And from that I can divide by 5 on both sides to make the number even a little smaller. 6 and the 5 here, which when we expand it, we get 18 and 6, 5 and 15. That we subtract and subtract on the other side, we get negative 9 dy dx equal 8 minus 15, that's 5 minus 18, that's 13. At the point 3 and 1, we get same thing, 13 over 9. The calculation, of course, on this step after we substitute is a little easier. So for the case we're not asking for dy over dx, but doing that is a little beneficial. Then for the equation, that y equals the slope times x minus the x0 plus y0. 13 over 9x minus 39. 13 over 9x. Negative 39 over 9 plus 1, that's just negative 30 over 9. Right, to get the equation, that will get is this thing. Right, so that is the case we can use when I'm not able to, or we don't need to find the dy over dx. We don't need to find the dy dx. We just find the tangent line. We could substitute the point in the middle. Right, so next time we'll find out the higher order derivative, and something require the logarithmic properties to find out the derivative. That's what we'll see next time.